All right, welcome to section 8.1, where we're going to be doing confidence intervals for single population means using the normal distribution. All right, let's start with an introduction here. Let's suppose you're trying to determine the average rent of a two-bedroom apartment in your town. You might look at the newspaper or internet or whatever and write down a bunch of rents and then average them all together. That average that you computed is called a point estimate of the true mean. X bar, that's the statistic we use for that, is your average and is a point estimate. This is a statistic. Mu, remember, is the true population mean. And to find that, we would have to find every single value in the entire population to compute it. So we don't compute this one generally. Generally, we just try to aim for the true population mean. Generally, it's uncomputatable. That's a word. All right. So what we're going to do now is instead of not just making an estimate for something, we're going to make a confidence interval that tells people how confident we are in our estimate. So the confidence interval provides a range of values in which we have a confidence or a confidence level that the value will fall. So let's look at an example. Suppose we consider the mean number of songs a consumer downloads a month from iTunes. We don't know the population mean, mu, because it's too many people to count and compute. However, to begin with, for this section, we're going to say we do know the population standard deviation is sigma, and in this case is 1. We take a sample of size 100 and calculate the sample mean, which is 2. I don't give you the data for that, but just trust me, I calculated the sample mean. It turned out to be 2 songs a month. And then by the central limit theorem, we know the standard deviation is going to be the population standard deviation divided by the square root of the sample size, which is 1 over 100, which is 1/10. So now let's remember what we know. We know the mean is 2, x bar is equal to 2. And we know that the standard deviation is 0.1 for this sample of size, I can't remember what it was. Was it 100? Yes. For the sample of size 100, the standard deviation is now 0.1. So remember, by the empirical rule, it says all 95% of the values are within 2 standard deviations of the mean. All right, so if we have our mean and we subtract off a standard deviation, that didn't arrow, that would be 2 minus 0.2, 2 standard deviations. That would be 1.8 for our lower value. And if we go up 2 standard deviations, so that's 2 plus 0.2, that gets us to 2.2. So using the empirical rule, we can say we are 95% confident that the unknown population mean number of songs is going to be between 1.8 and 2.2. And we get that confidence from the empirical rule telling us that 95% of the data is going to be within 2 standard deviations of the mean. We call this a 95% confidence interval. 95% of the time, our mean value is going to be in there. So how do we calculate confidence intervals? Well, let's talk about the setup. What we don't know is the population mean. What we do know is the sample mean, the number of items in the sample, the population standard deviation, and the desired EBM. EBM stands for error bound for population mean. Sometimes it's also referred to as margin of error. That's a more general term. We'll abbreviate it EBM. And when we have a confidence interval, it will have the form of our point estimate. So our X bar minus our error bound, comma, our point estimate plus our error bound. Let's talk about confidence levels for a second. So confidence level is the probability that the confidence interval will contain the true value of the population parameter. So for example, I am 95% confident that mu is between 5 and 9. My confidence level is 0.95. Alpha is the probability that it won't contain the true value of the population parameter. So alpha in this case is 5%. I'm 5% confident that mu is either less than 5 or more than 9. And alpha plus CL have got to be equal to 1 because it's either between 5 and 9 or it's not. So let's do an example. Let's say in this example, we're given the sample mean is 7 and the error bound for the mean is 2.5. That means my confidence interval is going to be my mean minus my error bound. So 7, my margin of error, 7 minus 2.5, which is 4.5. And my upper level of my confidence interval is 7 plus 2.5, which is 9.5. So if you're given the error bound and the mean, you can calculate the confidence level. We estimate with 95% confidence that the true value of the population mean is between 4.5 and 9.5. So let's do an example. Let's suppose scores on exams and statistics are normally distributed with an unknown population mean, unknown, and a population standard deviation that is known to be 3. A random sample of 36 scores is taken, and gives a sample mean. So we compute that of 68. Find a confidence interval estimate for the population mean exam score. So the mean score on all the exams. We want to find a 90% confidence interval for the true population mean of statistics exam scores. So what do we know from this example? Well, let's write down what we know. We know X bar is 68. We either computed that or somebody told us it was that. We know our sample size is 36, and we know our population standard deviation is 3. So we can find the sample mean standard deviation to be 3 over the square root of 36, which turns out to be a half. So we know the averages for the statistics exam scores is distributed normal with a mean of 68, the same mean, and a standard deviation of 0.5. So let's look at a normal distribution with a mean of 68 and a standard deviation of 0.5. What we need to do to find our confidence interval is we need to find these edge values here and here so that 90% of our data is between them. Then we'll be 90% confident that our exam averages will be in there. The average of our exam scores will be between those two values. All right. We know normal distributions are symmetric. So if we want to be 90% confident, that means we need 5% to the left here and 5% to the right and 90% in the middle. All right. Well, we know how to find, going back, let's just make sure we note that. If we want 5% here, that means this is the 95th percentile. I went too fast. If we want 5% below, we know this is the 5th percentile. Okay? So we can calculate the 95th percentile of this normal distribution. We know how to do that. We can calculate the 5th percentile of this normal distribution. We know how to do that on Desmos. So we go inverse CDF, normal dist, 68.5, 95th percentile, and we get 68.8224 about. And if we look at the 5th percentile, we get 67.177, maybe 6. And we know that that's the 5th percentile and the 95th percentile. So 90% of the data is going to be between those two numbers. So our 90% confidence interval is 67.1776 to 68.8224. Our mean was 68, so we can calculate 68.8224 minus 68, and we see that we went up 0.8224, and we can calculate 68 minus 67.1776, and so we went down 0.8224 also from the mean to get those endpoints. So our error bound for population mean, also known as the margin of error, is 0.8224. It's going to be the value between those two guys. We are confident that for 90% of the unknown population means of exam scores is between 67.1776 and 68.8224. All right, so let's do another example. Let's find a 98% confidence interval for the true population mean of specific absorption rates for cell phones. Let's assume that the population standard deviation is sigma 0.337, so somebody gave you that. Well, the first thing I'm going to do is I'm going to add up all these specific absorption rates, and there are 30 of them, add them all up, and divide by 30, and I calculate this to be 1.025. All right. I'm also going to note that the N is 30 in this case. There was 30 of those. They told us the population standard deviation was 0.337, and we want a 98% confidence interval, so our confidence level is 0.98. Now, we could continue as we did before, find the normal distribution for this, calculate the sigma over the square root of n, go in and calculate the percentiles that we need. So in this case, it'd be the 99th and the 1st. Find those, get their endpoints. You could completely do it that way. It's a little bit tedious, and the first reason I did it that way in the first place to really give you a picture of what we're doing. There are some really handy online calculators that pretty much do this for you. So let's go ahead and look at one of those. Here's the link. It's also in the top of MyOpenMath under resources. I'm going to go ahead and open that up for you guys. I have it right. Oh, I thought I had it open. Well, let's go ahead and just click on it. Maybe it'll open for us. Here we go. All right, so here is this calculator, and let me just make it a little bit bigger so you guys can see it. What was our confidence level that we were interested in? Well, we wanted a 98% confidence level, so I put in 0.98 for my confidence level. I've done this on one sample, and I'm going to input sample statistics. You could put all the data values if you want, but we've already computed the sample statistics. What distribution type do we use? Normal. That's all we've talked about. We're going to be doing student T in 8.2. What is the population standard deviation? 0.337. That was given to us. And our sample size was 30. And our sample mean, I don't remember, 1.025. So it's going to go behind the scenes and do all the stuff that you would normally, this is annoying, that you would do. I'm pushing the wrong way. That's the problem. It's going to go and do all exactly the same things we just did. Find the normal distribution, find the percentiles based on what you set your confidence level to be. But it's a little bit faster. It's not so many calculations for you. You hit calculate and the results come up here. It says a 98% confidence interval is 1.025, which was our mean, plus or minus this computed margin of error, 0.1508 or 1509. Okay, that's not what I got in this one. What did I do wrong, guys? 30, 98. Hang on, I typed something in wrong. 0.337. Oh, why is this 27? I must have bumped that. Let's try this again. 30. Calculate. I think I must have scrolled. Aha, that looks better. 98% confidence interval, 1.025 plus or minus 0.1431. All right, so I actually copied and pasted those results into my show here. So let's keep going. This is the results you got from using the confidence interval for a mean online calculator. So to find my confidence interval, I computed 1.025 plus 0.1431, and I got 1.1681. And I took 1.025 minus 0.1431, and I got 0.8819 for my confidence interval. Right? And you're welcome to use this confidence interval calculator online. It really saves a lot of computation. So let's think about what we just did here and make sure we feel good about what we did. We know that our means are distributed 1.025, and then this is our sample standard deviation. That's that 0.337 divided by the square root of 30. And we found endpoints so that our shaded area will be 98% of the probability. So this will be the first and 99th percentiles. And you can check your work by putting in your confidence interval, 0.8819 to 1.1681, and seeing that we do have 98% of the data falling in that range. So all the online calculator helped us do was just do those inverse CDF computations a little bit quicker, a little bit easier. All right, so we are 98% confident that the unknown mean of SAR level is between 0.8819 and 1.681 watts per kilogram. All right, so let's talk about just the effects of changing different things in our confidence levels. So if we increase our confidence level, that means we're going to increase our error bound and we're going to make our confidence interval wider. So increasing the confidence level would be like, oh, I was 90% confident, but now I'm 98% confident. Since you're more confident, you have more range of values because you have more range of values. You have a wider range of values, so you're more confident the mean is likely to fall in there. When you decrease your confidence level, if you go from 98% confident to 90% confident, you have a smaller range of values that could fall in there, right? So it makes sense if you think about it carefully. If you're more confident, because we're given a wider range. If you're less confident, it's because there's less range. This is similar to talking about changing the sample size. If you increase your sample size, this is going to make your standard deviation smaller, which causes the error bound to decrease, which makes your confidence interval smaller. If you decrease your sample size, this is going to make your error bound wider and your confidence interval wider. So let's think about our test score example just quickly. Remember our sigma there was 3. If we did a sample size of 36, we'd be dividing by 6. 3 by 6 is a half. If instead we did a sample of 100, we would divide 3 by square root of 100, which is dividing by 10, which is 0.3. So our standard deviation gets smaller with a larger, more data, which is what we saw when we talked about sample means as well. The more data we have, the more narrow our standard deviation is because we're averaging more things. We have more information, so the range is less broad. Let's look at a picture of what I'm talking about here. Here are two 95% confidence intervals, both with a mean of 68. Here is when I had 100 samples, I get to be 95% confident it's between 67.5 and 68.5. because I have more information. When I have less information, I have a wider range for the same level of confidence. Well, I only have 36 scores, so I'm only confident between whatever this is, 67 point something and 2, not quite 67.2, and 68.8 or something, right? I'm less confident because I have less data. All right, let's talk about the last thing we need to do in this section, and this is sample size. So let's say the population standard deviation for the age of Foothill College students is 15 years. And we want to be 95% confident that our sample mean will be within 2 years of the true population mean age of Foothill College students. How many randomly selected Foothill College students must be surveyed? So this is like how many, what do we want to set our N to be for a particular confidence level and a particular margin of error, okay? In this case, our margin of error is we want it to be within 2 years and we want to be 95% confident. So we need to figure out the N value that will put us into this range. There's a calculator for this as well. There's a hard way to do that, but this is definitely the easy way. So let's go to this calculator. Oh, it actually worked there. The link for this is also in the same place in the resources. So we're going to make an estimate for mean this time. Our population standard deviation was 15. That was given to us in the problem. And they said our margin of error, we wanted to be within 2 years. So that's going to be 2. And we wanted a confidence level of 95%, so 0.95. So we hit calculate, and it says 216.082. I'm going to sneeze. Excuse me. Pardon. All right, so that's my sample size I need to get for my confidence level to be 95% with the population standard deviation of 15. That means I need to do a sample size of 217. On these, you are always, always, always going to round up because it's one of those things. You're not going to hit that 95% confidence level if you had 216. You just a smidge under. You got to be more than you would be confident. So you always round these values up. All right, that's it for section 8.1.